So there's two main things that I want to talk about today. And the first is telling you about all of these interesting optimizations of garbled circuits, optimizations to make them smaller. So I summarized them all in this diagram. And the y-axis on this diagram is the number of bits per gate of a circuit. And these different lines are for different circuits. Just there's nothing special about these 4 circuits, just 4 different standard circuits that are easy for us to obtain. So people have posted these Boolean circuits on their websites. So when we measure garbled circuits, we use these standard benchmarks. And so these different optimizations work differently for different particular circuits. So the main thing today is to tell you about these different optimizations and how they work, and how they make garbled circuits so small. But this is all talking about Boolean circuits. So even in that first slide, the example that I showed was a Boolean circuit, and that makes sense because Boolean circuits have gates with the smallest truth table, and we're really encrypting the truth table. So Boolean circuits make sense. But another natural way to express a computation is arithmetic circuits. So arithmetic circuits, the wires in an arithmetic circuit are not just 0 and 1, they can be values from a ring, and you can have gates for adding values and for multiplying values. So think of a large ring like maybe integers mod 2 to the 32, something like that. The results for Boolean circuits don't really apply to arithmetic circuits. So we need completely different techniques. And I'll talk about some of my recent work on garbling arithmetic circuits. And I'll try to tell you the state of the art for arithmetic circuits. Okay, so we'll just jump right into the technical details. So one thing that some of you noticed last time is that if I arrange the 4 ciphertext for a gate like this, the position of those 4 ciphertext leaks some information about the truth values. So see, I've arranged these 4 ciphertext in a very predictable order with 0, 0 first and 1, 1 last. And we want to hide whether the wire labels are 0s and 1s. So we have to actually permute these 4 ciphertext. That was something that, you observed last week. I didn't include it in my slides last week, but it is something that needs to happen. So when someone is garbling a circuit, they generate these 4 ciphertexts. They need to randomly permute those 4 ciphertexts, okay? And what that means is that the person who evaluates this garbled circuit has to try to decrypt all 4 ciphertexts until they find one that where the decryption succeeds. So I'm making the assumption that when you try to decrypt some of these ciphertexts with the wrong keys, for example, if you have A1 and B0, you should be able to decrypt this 3rd ciphertext because you have the correct keys. But if you try decrypting these other ciphertexts with the wrong keys, you should get some sort of error. So the encryption scheme should have that as a feature. It turns out that this is a source of inefficiency in garbled circuits. So the first thing that I want to show you is a way to avoid that problem. Okay. Why does this have anything to do with the size of the garbled circuit? It's because you need a ciphertext that has some redundancy in it. So you need a way to detect whether decryption succeeds or fails. You won't be able to tell that just by looking at the output, right? Even if decryption is successful, you will learn a wire label, which is some random string. So it's not like you're decrypting a ciphertext and you expect to see Chinese text and then you just see something else. No, you are decrypting and you expect to see something that looks random. So we can't use the plain text to help us here. We need to add extra redundancy to the ciphertext. Maybe some sort of a message authentication code, something like that, so that we know that we have the correct key. Basically, that means the ciphertext needs to be longer than these wire labels. In particular, if the wire labels are 128 bits, you probably need ciphertexts that are 256 bits long. So each of these ciphertexts is maybe 256 bits long. All right. So this first optimization that I want to share is an old one from Beaver, McCauley, and Rogaway in 1990. And they had this nice observation. They said, what if you took every pair of wire labels, let's take A0 and A1. I'm going to color one of them red and one of them blue, but I'm going to choose red and blue at random, right? So for this wire, the 0 label is red, but for this wire, the 0 label is blue, okay? So there is a random association between the colors red and blue and the values true and false. For every wire, it's independently random. And now I'm going to say that when the evaluator looks at a wire label, he will know what color it is. He will know whether it's a red label or a blue label. So you can think of using the last bit of this string. If it's a 0, that means red, and if it's a 1, that means blue. Okay, and remember, so a wire label doesn't reveal its subscript. So in my notation, the subscript tells you whether the wire label encodes true or false. That should be secret. If you're looking at a wire label, you should have no idea whether it's the 0 or the 1 wire label, but you should know whether it's red or blue. Okay, so if we have wire labels like that, then we can rearrange these ciphertexts according to their colors, not according to their subscripts or true and false. So this is what the 4 ciphertexts look like if I arrange them according to true and false. But Beaver, McCauley, and Rogaway say, don't do that. Instead, you should arrange them by the keys in some standard way. So maybe in my world, we always put the red ciphertext first, and then the red blue ciphertext next, and so on. Okay, so hopefully that is clear. So instead of shuffling them randomly, we shuffle them predictably according to these colors. But so this is the Garbler's view. So you should get used to this. I'll always show the Garbler's view and then show the evaluator's view. So if the evaluator comes across this gate, maybe the evaluator has A1 and B1, he doesn't know that this corresponds to true and true on the 2 wires, but he knows that it's blue and red. So he knows that blue and red is always in the 3rd position. And so that's the ciphertext he decrypts. He only has to decrypt that one ciphertext. He doesn't have to try these other 3 ciphertexts and see if it succeeds or fails. So what that means is that we can use a simpler encryption scheme. In fact, it just needs to be a one-time encryption scheme. So previously I used this notation, encrypt the plain text C using keys A and B. The way we do that is just, for this talk, let's just imagine we have a random oracle. So if you have a random oracle, then use H of A and B as a one-time pad to mask the plain text C. Okay, so I've drawn that up here in the garbled gate. I hope you can see that still. But there's no redundancy in these ciphertexts. I just want to emphasize that. So if a wire label is 128 bits, then the ciphertext, each of these 4 ciphertexts is 128 bits, right? And hopefully it makes sense that you can use a one-time encryption, because garbled circuits can only be used once. And when you use this garbled circuit once, you only evaluate this gate once. Okay, so hopefully that kind of makes sense. So this is a nice simple trick, and here is the result of that trick. So in the classical scheme, the original Yao's construction, the size of the garbled circuit for each gate, there were 4 ciphertexts, but they each had to be, like twice as long as a wire label. So I'll give that a score of 8. But now each of those 4 ciphertexts is just exactly the same size as a wire label. So now the score is 4. I'm going to show this scoreboard many times throughout the lecture, and we'll see this number go from 8 to 4 to something much smaller. And we'll focus on this first column, just the size of the garbled circuit. Like I said, that's the most important parameter for garbled circuits. But in case you're interested, I also listed how much does it cost to garble each gate, how much does it cost to evaluate each gate. And I'm measuring this in terms of the number of calls to a cryptographic function like AES, for instance. Okay, so that's our first optimization. It's kind of a nice idea. Let's see where we can go from here. If I think back to when I first learned about garbled circuits, well, I first learned about them, in grad school, but I didn't think about it very much. But when I first learned about how to actually implement garbled circuits, this was many years ago, I guess, 2013 probably. Trick. If you think about these garbled gates, you're encrypting a truth table, and the truth table has 4 entries because there's 4 possible input combinations to a Boolean gate. So it makes sense to me that when you encrypt the truth table, you have 4 entries, 4 ciphertexts, 1 for each row of the truth table. And then I learned that, back in 99, Naor, Pincus, and Sumner figured out that actually you don't need 4 ciphertexts, you can do 3. And I thought that was amazing. It was very surprising to me. Of course, 3 is only the tip of the iceberg. We'll make these much smaller than 3, but yeah, I think it's nice to remember that yeah, these tricks can be very surprising. Okay, so here is the standard garbled gate, and we're using point and permute. I realize I didn't mention the name of this previous technique. Is called point and permute. Sometimes I'm calling these color bits. So every wire label has a color, red or blue. And those are bits that point you to the correct place in the garbled gate. And the items in the garbled gate have been permuted according to these colors. Okay, so that's why it's called usually called point and permute. Sometimes these I call them color bits, but sometimes people call them permute bits or pointer bits, something like that. So you may see them called different things. Okay, so here's a standard point and permute garbled gate for this particular gate. Everything is fine. So the new idea here is to think back about where these wire labels come from. So when I first described garbled circuits, I said for every wire in the circuit, you should choose a false label and a true label. Okay, and the idea behind this trick is that you don't need to choose these wire labels uniformly, okay? Instead, what if you choose the wire labels in such a way that the first ciphertext is all zeros, okay? That's a very strange thing to say, but let's just imagine what would be required to make this ciphertext that I highlighted be all zeros. Well, the way to do that is to choose C1 to be equal to this H of A0 and B1, right? If I choose C1 in this way, then the result of this XOR is all zeros. I think you can agree with that. Okay, and maybe if the point and permute bits were different, if these color bits were different, then a different one of these ciphertexts would be first in the list. And so maybe I wouldn't choose C1 to be this value. Maybe I would choose C0 to be equal to, one of these three outputs of H. Okay, so that's why I say I always want the first ciphertext to be all zeros, but which ciphertext is first, that depends on these color bits. And to make the first ciphertext 0, I either choose C0 in a certain way or C1 in a certain way, right? So that depends on, the specifics of the truth table and these color bits. Okay, so now I've done that. I chose C1 in this way instead of choosing it uniformly at random. And now this first ciphertext is all zeros, okay? But if I'm garbling a circuit and you know that I'm going to choose the wire labels in this way, it's wasteful for me to just send you all zeros. You know that I chose the wire labels so that the first ciphertext is all zeros. I don't actually have to send it to you, right? It's redundant. It's public knowledge that the first ciphertext is all zeros. So instead, I will just send you 3 ciphertexts. And then when you evaluate this garbled gate, you know the other 3 ciphertexts, and you will just imagine that the first ciphertext is all zeros and then do the usual pointed permute evaluation, right? So you can reconstruct this missing ciphertext in your head. It's always the all zeros ciphertext. Yeah, this really surprised me and delighted me when I first learned about it. You might ask, well, does it compromise security if I choose C1 in this way? So if you think about it, yeah, let's go back here. If the evaluator has A0 and B1, then he's supposed to learn C1. Okay, so this is fine. Yeah. If the evaluator is supposed to learn C1, then we worry about C0 being hard to guess. Okay, well, of course, C0 is still hard to guess. But imagine if the evaluator is entitled to learn C0. So that means the evaluator can decrypt one of these 3 ciphertexts. Well, we were already saying that in the normal point and permute, we're already saying that if you're supposed to learn C1, then you could never guess this hash value, because if you could, then you would learn C0 and C1. That would break authenticity. So within the security proof of just the normal point and permute garbled circuits, it's already showing you that this hash value is hard to guess for somebody who is supposed to learn just C1. So that means that this value is just as good as random to somebody who's supposed to learn C0. This is not a formal proof, but that's a justification why it's safe to do this, right? Even when you choose C1 in this way, it still is secure enough, I guess. So I hope that made sense. If it doesn't, please ask in the chat and we can clarify. Another consequence of this trick is that the circuit has to be garbled in order. So you have to start at the input labels, right? So another way of saying that is I don't know what C0 and C1 will be until I start garbling this gate. So I have to garble the gates in order. Whereas previously, I could choose all the wire labels first, and then I could garble every gate independently. So now the gates are no longer, the wire labels are no longer independent. So that's not a bad thing, it's just an observation. Okay, so this technique is called garbled row reduction, sometimes called GRR, garbled row reduction. So like I said, we reduce the size of the garbled circuit from 4 to 3 ciphertext. And in this table, I called it GRR3, which probably makes you wonder, oh, is there another GRR with a different number? Well, yes, there is. Which I will show you after the break, I guess. So another nice trick, this is maybe the most famous optimization to garbled circuits, and it's due to Vlad Kolesnikov and Thomas Schneider. And it's an optimization for XOR gates. So I'll try to motivate XOR gates by thinking about these wire labels in a different way. So previously we're just thinking about the false label and the true label. Those are the important things on a wire. I want to introduce a new value on the wire that's also important, and that's just the XOR of these two wire labels. So I'll say that the offset of this wire is A0 XOR A1. And then instead of writing the labels as A0 and A1, I'll write them as A0 and then A0 XOR the offset. And every wire has a different offset. So I'll write delta A as the offset of this first wire, and delta B is the offset of this next wire. So A is the label that means false, and A XOR delta is the label that means true. Okay, so far I haven't changed anything. It's maybe a change of basis, but I haven't changed anything. The free XOR trick says, let's make sure that all the wires in the circuit have the same offset. Okay, so now this delta value is global. Every wire in the circuit has two wire labels whose XOR is this delta. Same delta for every wire. Now, why would we want to do this? Because if you look at an XOR gate, if you look at an XOR gate, instead of choosing the output false label randomly, let me back up. There's only, once I choose delta, that's fixed for every wire in the circuit. So the only degree of freedom left on each wire is the choice of its false label. So like C is the false label on this output wire. And now when I have a XOR gate, instead of choosing this output label randomly, I will choose it to be the XOR of the two input labels. So A plus B in this case. I think that's what I wrote here. And now something nice happens. So imagine that you're evaluating the circuit, and so you know one of the possible labels for each wire, each input wire. What happens if you XOR them together? So if you have A and B, that encodes false and false. You XOR them together, and you get something that encodes false on the output wire. If you have false and true, you XOR the labels together, you get the output label that encodes true. Same for true and false, and same for true and true, right? So the XOR delta cancels off here. So what this means is, if the wire labels have this property, meaning all wires have the same offset, and the output wires in an XOR gate have this relationship to the input wires. If that's true, then you can evaluate this gate just by XORing the input wire labels. I don't have to send you any garbled ciphertext. I don't have to send you anything. And you don't have to do any crypto operations. You don't have to decrypt a ciphertext. You just XOR your gates together. That's why it's called free XOR. So using this technique, XOR gates can be free. Free in terms of communication, which is what we're measuring here today. Okay, so now the scoreboard has gotten more complicated, because now I need to make a distinction when I'm talking about the size of a gate. XOR gates and non-XOR gates are treated differently. Okay, so previously every kind of gate was treated the same way. Well, now free XOR says you could treat the XOR gates differently. Now they cost 0. Okay, but we still have to do the usual thing for the AND gates. I hope that makes sense. Let's see. Okay. One thing that you can see in this slide is that compatible with this garbled row reduction, right? So I didn't say that XOR gates are free and AND gates cost 4. I said XOR gates are free and AND gates cost 3. And I don't have a slide to explain why they're compatible, but maybe you can think, that's an exercise for you maybe to think about why those two techniques are compatible. Okay, good. So one more nice trick. This is a fancier version of row reduction. Okay, so again, I'm going to start with the standard point and permute AND gate that costs 4. Okay, and I'm going to take this reasoning to the next step here. So previously I said, well, don't choose these output wire labels randomly. Choose them to make the first ciphertext all zeros. Okay, so we do that here. That's the same as before. Now there's a new trick. I can choose one of the labels to make the first ciphertext all zeros, and I can choose the other output wire label so that the XOR of the other 3 ciphertexts is all zeros. So that's interesting. So you can check in this case, if I choose C0 to be the XOR of these 3 hash values, and then I XOR all 3 of these ciphertexts together, everything goes to 0. So hopefully you can verify that in your head. So what this means is if the garbler and the evaluator agree that the garbled circuit is generated this way, it means you don't have to send the first 2 ciphertexts, right? If I just send you the last 2 ciphertexts, then you know that the first one should have been all zeros, and you know that the second one should have been the XOR of the other 2, right? This is, sorry, the second ciphertext has to be the XOR of the last 2. That's the only way that all 3 of them would XOR to all zeros. So this is a nice trick. It's due to Guerra and Lindell, Nof and Pincus. This works for, so the fact that you can do this step, the XOR of the other 3 ciphertexts being 0, that only works for things like an AND gate. It has to do with the fact that in this truth table, there will be 3 zeros and 1 1, 3 falses and 1 true. If there's 2 falses and 2 trues, then this trick doesn't quite work because things cancel out with each other. There was a previous construction that got AND gates down to 2 ciphertext, but it's much more complicated. This one is much easier for me to explain. Okay. So that's garbled row reduction, getting down to 2 ciphertext. The problem is that, so there's another way to get AND gates. I showed you how to get AND gates to work, but there's something similar that works for XOR gates. But these techniques are not compatible with free XOR. So now at this point in history, we had a problem because you could use free XOR and you could pay 0 for XOR gates, 3 for AND gates, or you could use this garbled row reduction and pay 2 units for every ciphertext. And sometimes one of the other was more efficient. So that was kind of a problem. So for some time it was an open problem whether you could get XOR gates to cost 0 and AND gates to cost 2, like at the same time. Yeah, and the reason these techniques were incompatible is that if you want free XOR, then you need to make sure that these 2 output wire labels XOR to a fixed value delta. But if we go backwards, in this example, this is how I had to choose C0 and C1 as the result of some XOR of some hash outputs. There's no way I can guarantee that these 2 values XOR to this delta that I care about, right? And so if the output labels don't XOR to delta, then I can't do free XOR. So that was the main problem with these 2 techniques. So this was an open problem that we and my co-authors, Sami and David, we resolved in 2015. Seems like a long time ago now. So we had this technique called half gates, and I'll explain what that means, but we were able to get free XOR and also have a ciphertext costs only 2 ciphertexts, or an AND gate only costs 2 ciphertexts. So I'll explain how that works. So it starts out with these 2 hypothetical questions. Yeah, so there's going to be like 3 steps to this. So the first step is this hypothetical question. So we are in the free XOR setting, so that's why I've drawn the wire labels to look like free XOR wire labels, the same delta everywhere. Could you garble this AND gate cheaply if you knew that, if the garbler knew that, if the garbler knew what the value was going to be on one of the input wires? So for example, at the time that you're garbling the circuit, you know that the value on this wire will always be false. So could you garble the circuit more efficiently then? Okay, so if you knew that this top input wire was 0, then this is an AND gate, so you know that the result is always 0. It's a constant, sorry, it's a constant function. So this is its truth table, right? It always gives output 0. And you could garble it in the usual way. You could say, well, I need to encrypt the value C under the key B, and I need to use B XOR delta to encrypt the value C. So that looks like this. Okay, that's how you would garble in that case. If you knew that the value on this wire was going to be true, then this AND gate becomes just like an identity function. So you need to garble the identity function. What does that mean? It means if the evaluator has B, they should learn C. And if the evaluator has B plus delta, then they should learn C plus delta. So we can encrypt C under the key B, and we encrypt C plus delta under the key B plus delta. Okay, those are the 2 choices. You can merge these 2 choices by saying, oh, the only difference is what I do right here, right? That's the only difference. So I can combine these into a unified thing. So if I know that the value on the top wire is little a is a bit here, then I would garble this garbled gate, I would say. Okay. But we know there's another trick. So that looks like the answer to my question is, well, you could garble this for 2 ciphertexts. But we have tricks that we remember. So we have a row reduction. Use it all the time in cryptography. It seems like it's very powerful. So I could say, instead of choosing this C value uniformly at random, I choose it so that the first ciphertext becomes all zeros. Okay, and then I could do the normal row reduction. There should be a point and permute here. There should be some color bits, but I haven't drawn them because it would make my picture too complicated. But basically the answer is, if the garbler knows in advance what value will be on a wire, then he can garble this gate for just one ciphertext. Okay, this is the entire garbled gate. Okay, now there's a similar question we can ask. What if the evaluator knows, I shouldn't say knows in advance, but what if the evaluator somehow knows, as they're evaluating the circuit, somehow they just know that the value on this wire is true or false? Can they use that information to make a more efficient AND gate? Right, okay. So let's suppose the evaluator has a wire label B for this wire, and the evaluator somehow knows that B means false. Okay, this is hypothetical, but the evaluator knows that it has false. And so since this is an AND gate, and you have false on one of the inputs, you should get false output label. Okay, so how do we do that? Well, if you have wire label B for false, you should learn the false output wire label C, right? So we encrypt C using B as the key. If the evaluator has the true wire label and they know that it's true, then again, this AND gate becomes like an identity function. Whatever value, true or false, is on this A input wire, that should be transferred to the output wire. And the way we can do that is, if the evaluator has the true wire label, we will let the evaluator learn this value A XOR C. And how is that useful? Let's suppose that we're in this situation. So the evaluator has A and A false and B true wire labels. He knows that he has the true wire label here, but he doesn't know he doesn't know whether this A wire label is true or false. But he decrypts this ciphertext and learns A XOR C and just XORs it with this A wire label, and the result is C. Of course, if instead he had A XOR delta, you would do the same thing and he would get C XOR delta. Right, so A XOR C is the information you need to translate the truth or the true or false value on this wire onto this output wire. Okay, so with these two ciphertexts, you can make an AND gate that can be evaluated in this weird way if the evaluator knows what one of what one of these wires in wire labels encodes, true or false. Just like before, we can do a row reduction. So instead of choosing C uniformly at random, we choose C so that this first ciphertext goes to all zeros. So that means we don't have to send it. So the answer to this question, what if the evaluator knows the value on an input wire to an AND gate? It turns out that we can garble that AND gate for one ciphertext. Okay, that's interesting. Now let's put these two observations together. Let's imagine that we want to garble an arbitrary AND gate in the circuit. Okay, it doesn't have any of these weird assumptions. I'm going to write this AND gate, A and B, in the following way. A plus R basically, and B. I'll use the distributive property and I'll get these two AND expressions. Okay, now what if the garbler is the one who chose this random bit R? It's a random bit. So the garbler knows R. And what if we somehow let the evaluator learn A, XOR R? And that should, so A is like the correct value that's on this wire. We don't want the evaluator to learn little a, but it's safe to let the evaluator learn A, XOR R because R is random. So this is like a one-time pad, okay? So now the garbler knows this random bit R, the evaluator knows this bit A, XOR R. They know these bits in the clear. But look, we have an AND gate where one of the inputs is known to the evaluator. We have an AND gate where one of the inputs is known to the garbler. That's this little r. So each of these AND expressions can be garbled with one ciphertext each. And then I just need to XOR the results together. So I have two of these. This is why we call them half gates. So half gates are things that you can garble for one ciphertext. And I have two of them. And then I have an XOR gate, and we are in the free XOR setting. So this XOR gate is free. So overall, the total cost for this this normal AND gate is the cost of two ciphertext. Okay, so that's how we do it. And it turns out that you might wonder, how does the garbler choose this random bit R? How do you let the evaluator learn A, XOR R? Well, actually, this A, XOR R can just be the color bit on the wires that we're already using. We already have color bits on the wires. These color bits, if you look at them a different way, they have this property. The garbler knows one thing, the evaluator knows the other thing, and they XOR to give you the actual value on the wire. So you don't even need to work extra to achieve these two properties. Okay, so that's half gates. Like I said, XOR gates are free and AND gates cost 2. That's exciting. So you might wonder, like, the size of these garbled gates is going down and down. Is there a limit? Like, is half gates the best possible way to garble a Boolean circuit, or could you do better? So in the half gates paper, we proved a lower bound. We said it's not possible to garble an AND gate with less than 2 ciphertexts. And then in later work, I was also a part of this work. I showed that, oh, actually, you can garble an AND gate with 1 ciphertext. So it looks like I contradicted myself. But actually, in the half gates paper, we showed that you can't garble an AND gate with less. You can't do better than half gates using standard techniques. So we looked at all of the techniques that were known up to that time, and we made this general model of garbling. And we said, in that model, you cannot do better than half gates. And then later, myself and then this other independent work by Kemka, Kikuchi, and Suzuki, both of these works show how to do an AND gate with 1 ciphertext by doing things that were not, new ideas that were not part of this model. The problem is both of these papers only showed how to garble a single AND gate in isolation. So what that means is if the entire circuit is 1 AND gate, then you can garble it with a cost of 1. But if there are multiple gates in the circuit, then these constructions don't work. It's very, very unsatisfactory, I would say. So there's still kind of a gap here. So that's the current state of things. So right now, the current open question for garbled circuits is whether we can do better than half gates, but in a useful way. Like, can you garble an entire circuit where the XOR gates are free, but the AND gates all cost less than 2? Currently, that is not known. So that's the open question here. Okay, I think that's the end of this section 1. I'm just checking the time. I think we're doing fine for the time. So that's basically everything I know about Boolean garbled circuits and how to make them smaller. If there are any questions now, this would be unmute and ask if you're there in the room, or you can ask on the chat. If there are no questions at this time, then I will move on to talk about arithmetic circuits. Okay, so I'll move on and I'll talk about arithmetic circuits next. And this is some joint work with Marshall Ball and Tal Malkin from a few years ago. So our main idea, yeah, let me just say that I love this paper because all of the ideas are very simple given what I've just showed you. But we were happy to be the first to put them together in the right ways. So I'm going to start by generalizing this idea of free XOR. So in free XOR, you have wires in the circuit, and the wire can contain a 0 or a 1. You have wire labels, which are bit strings, and you have this offset, delta, and the offset just means the XOR of the false wire label and the true wire label is delta. So usually you write the true wire label as A XOR delta, the same delta for every wire in the circuit. So it's possible to generalize free XOR in a very natural way. So imagine you had a circuit where the wires were not just bits, but they were values from integers mod m. Okay. Then you could let wire labels, instead of being strings of bits, they could be strings of integers mod m. And if wire labels are strings or tuples of integers mod m, then their offsets would be also a string of integers mod m. And we could encode different values using related wire labels. So there's a wire label A, and then there's A plus delta, and then A plus 2 delta, A plus 3 delta, and so on. So this capital A is a wire label. It's like a vector of integers mod m. So is delta, but little a is just a scalar, a single value mod m. And the wire label for the value little a is capital A plus little a delta. Okay, and the plus here is it's addition of vectors mod m, right? In the same way that XOR is addition of vectors mod 2. Okay, this is pretty decent. Okay, but this is good. Yeah, so here's a summary of what I just said. The value little a on a wire has this wire label. Okay, so if you have a gate like this, so this is a gate for addition mod m. So you have like little a and little b, and you want to add them mod m. Well, just like in free XOR, you can get this for free if you have wire labels of this kind, right? So if the evaluator, let's imagine what would happen if the evaluator just adds these wire labels. So if you add these wire labels, you get something that looks like this. All these pluses are like addition mod m. So if you choose the base output wire label for the output wire to be a plus b, then right in this expression, it looks like you've got a wire label that encodes the value a plus b, right? If you follow this guide right here, then this output value looks like a wire label that encodes a plus b, and the plus is addition mod m. So we've generalized free XOR to give free addition mod m. So that's reasonable, I hope. You can also get free multiplication by a constant if the constant is relatively prime to the modulus. So this is something that you wouldn't notice from free XOR, because in free XOR, the modulus is 2, it means that you can multiply by a 1. So that's not very interesting. But imagine if you have free addition mod 5, then you also have free multiplication by 2. There's a question in the chat. Thanks for that. Why are the labels a vector instead of just a value? That's a good question. So just like in free XOR, the value is just a 0 or a 1. The wire label has to be something long that you can use as an encryption key. The same thing is true for this generalized version. I want you to think of little m as a small number like 5. So the wire label has to be, it still has to be an encryption key. It has to be a cryptographic key that you use for encryption. You can't just use a number from 1 to 5 as an encryption key. So you need to do a longer value, but we also need these values to be compatible with addition mod 5, right? Just like in free XOR, we needed the wire labels to be compatible with XOR. Here we need them to be compatible with addition mod 5. So that's why they're vectors of mod 5 values. Good. Okay, so if you have wire labels of this kind, you can get free addition mod m. You can get free multiplication by a constant. You can also garble unary gates. So unary gate just has one wire coming in and one wire coming out. The interesting thing here is that you can have a gate where the value coming in has a different modulus than the wire coming out. So I want you to imagine a circuit with many different wires, and each wire has its own modulus. That's the kind of circuit model that we support. So garbling a unary gate is easy. Like, here's the truth table of this unary gate. If you have input 0, you get output 5, 0. Now you have these wire labels on the inputs and outputs, and you can arrange them in the usual way. If the evaluator knows A, they should learn C plus, sorry, if the evaluator knows A, they should learn C plus 5, 0 delta. Since the modulus might be different on the input and output wires, and so the offset delta might be different. You have one offset for each modulus, right? Yeah, all of the mod m wires have to have the same delta, so you can add them together for free. But you'll never try to add a mod m value to a mod l value. You don't get that for free. So in any case, you just encrypt in the normal way. So the cost of this garbled gate is m ciphertexts, because there's m entries in the truth table. You can reduce that to m-1 using a standard row reduction trick. So the way I like to think about it is you have 1 degree of freedom in how to choose this output label C. So choose C to make this first ciphertext go to 0. There's also a pointed permute that has to happen, right? You realize that I can't, when I garble the circuit, I cannot list the ciphertext in this order. It's being ordered by the truth value. So I have to have a point and permute, and instead of just 2 colors, now there should be m colors. So it's not a color bit, but the color is like a mod m value. And so I permute these ciphertexts. Actually, I do a cyclic shift of the ciphertext according to this these color values. But I don't have enough colors to draw them, so I don't draw them in this picture. Okay, so to summarize what we have, it's all just very simple stuff. We generalize free XOR, and we can garble a circuit where you have different wires that have a different modulus. Every modulus has its own global offset that relates the wire labels to each other. I can garble an addition gate for free if all of the wires touching the gate have the same modulus, right? So I can add as mod m, and get a mod m result. That's free. I can multiply by constant. That's free. and I can do these unary gates, and that costs m minus 1 ciphertext, where m is the modulus of the input wire. So just using these tricks, we can do some amazing things. So yeah, I'll try to convince you that this is, for some computations, using this set of ideas, even though all of these ideas are very simple, this gives you a much better performance than a Boolean circuit. So let's imagine you're doing some secure computation task that involves lots of additions and multiplications on 32-bit values. It's a natural thing. 32-bit integers. Okay, so most of the cost of the computation is additions and multiplications. So if you converted that into a Boolean circuit, you would have lots of little addition circuits, lots of little multiplication circuits for Boolean values. Here's a different way to do it. Okay, yeah, that's the standard approach, is to turn this problem into a Boolean circuit problem. And for Boolean circuits, you garble with this half gates technique, and you pay 2 for every AND gate, and you pay 0 for an XOR gate. Okay, so if we're talking about 32-bit values, here's how much each of those operations cost. So adding 2 32-bit values, they cost 62 ciphertext using half gates. Multiplication costs 1,200 ciphertext. Right, I had a student find a good multiplication circuit for multiplying 32-bit values, and apparently it had 600 AND gates. So the cost to garble it was 1,200 ciphertext. Okay, this is our benchmark, and I want to do better than this benchmark using these tricks. Okay, so imagine an arithmetic circuit where instead of the wires being 0 and 1, the wires are values like 32-bit integers. So using these tricks that I just showed you, we can do addition and multiplication by a constant, and they are free. So that's good. So I can have a 0 here. How can we do a multiplication? I didn't really describe how to do multiplication. It turns out there's a way to generalize half gates. So half gates is like multiplication mod 2, and it costs 2 ciphertext. So it's possible to generalize half gates to do multiplication mod m. It costs 2m minus 2 ciphertext. Well, that's very bad here, because m in this case is 2 to the 32. So actually this is looking really bad. And if this was the result in our paper, then it would be embarrassing for me to present it to you. So let me describe how to do things a little bit better. So this is a funny slide. The previous slide involved doing arithmetic mod this number. This number is 2 to the 32, right? So this was a garbled circuit, an arithmetic circuit, where the modulus is 2 to the 32. If we didn't use 2 to the 32 and we used a different modulus, we might have a better performance. And I don't know if anyone recognizes this number. It's not a number that I would recognize, but it turns out this number is the product of the first some number of primes. The product of the primes up to 29. Okay, so why would we want to do this? Maybe you can predict where this is going. Okay, I just have to, I have an awkward situation because here in America, we call this the Chinese remainder theorem. And I don't know exactly what it's called for those of you living in China. I know a little bit about the history of it, but yeah, here in the West, it's just called Chinese remainder theorem. So probably probably you're familiar with people calling it that. I think there should be a better way, a bit more credit to the individuals behind it. But in any case, I know it as the Chinese remainder theorem. Yeah, thanks for sharing the name in the chat. Unfortunately, I don't know how to read that. Okay, so instead of representing numbers in binary, you should represent them in a residue number system, okay? So you can represent a number x by its remainder mod 2, and its remainder mod 3, its remainder mod 5, and so on, okay? So the Chinese remainder theorem says these values, this set of remainders, uniquely determines the value x up to a certain number, which is the product of all these moduli, right? And we can take advantage of this garbling technique. The garbling technique supports a circuit where different wires have a different modulus. So we can have mod 2 wires in the circuit, and we can have mod 3 wires, mod 5 wires in the circuit. And the great thing about this Chinese remainder, do arithmetic on this number x, then you could just do the operation that you want individually in each modulus, and you get the right answer. Okay, so it turns out when you do this, so instead of representing a number as a value on a single wire, and the modulus on that wire is 2 to the 32, I will represent that value as a collection of wires. I don't know how many primes there are. Let's say it's 10 primes. I will represent that number using 10 wires. Each of the wires has a different modulus. Then if I want to add, I just add locally within each modulus. If I want to multiply two values like this, I just multiply their mod 2 component, multiply the mod 3 component, and so on. Remember, the cost to multiply things mod m is roughly 2 times m. So actually, I get this much nicer expression here. And so this is, you can see this is much better than just the standard Boolean representation. So that's the main idea of this paper that I'm discussing, is these really simple tricks that generalize free XOR, and then you should represent numbers in this residue number system using Chinese remainder theorem. Okay, so that's the big picture. If you represent your values in this residue system, then addition and multiplication is cheap, even for large numbers like integers mod 2 to the 32. It does cost something to get values into this residue form. Some of these are not there. It says not so good. I think I should say not so bad. Converting from binary into this form is okay, and getting the input values in this form is okay. But if you want to compare two values, like imagine that you have two large values that are represented in this format, and you want to compare which one is larger, that's actually very difficult. And if you want to convert back to binary, that's difficult. If you want to divide, it's difficult. If you want to do like a modular reduction mod 2 to the 32, that's also difficult. So this representation naturally works modulo this modulus. But if you want to work, like if you want to do garbled RSA, then you need to reduce values mod some other big modulus. That's expensive in this technique. So let's see how we're doing for time. Yeah, I think I have some time to go into a few of these technical details. I will skip this one though. I'll talk a little bit about how we compare these values. So here's the usual view of this residue system. So on the right is, all of the usual numbers, the usual representation of a number. And on the left is how they get represented in this residue system. So here is the number mod 2. The next column is the number mod 3. This is the number mod 5. This is the number mod 7. Right? So you can see what's going on here. That's the usual view. And like I said, this is a bad representation to compare two integers. Here is a better representation. So this is a positional number system. So here I have a ones digit, right? So I count, I go 0, 1, and then I wrap around, and now I carry into the next position. This is a twos digit, right? So this is the number 2, this is a twos digit. I add 1, and that keeps incrementing. This twos digit is a number, the value in the twos digit is 0, 1, or 2. And once it goes beyond 2, then it carries over to the next position. So this is like the normal base system, but the different digits have a different modulus, right? So the ones digit works mod 2, the twos digit is mod 3, the threes digit is mod 5, the fives digit is a value mod 7. This is called the primordial mixed radix. So mixed radix means, it's not 1000th digit. It's mixed. They're different, different possibilities in the different digits, and primordial because it's the product of the first few primes. If we had numbers represented in this form, primordial mixed radix, then it's easy to compare them, right? Because it's the normal way of comparing numbers. You look at the first position where they disagree, and then you see which one has the larger digit. So it's a positional number system where there's like a value for each digit. So that's easy. So all it takes is to convert these residue representations into this mixed radix representation. So this is tricky. We spent a long time figuring out a nice way to do this. So here is how you represent a number in this mixed radix. So you have a twos digit, and this is the ones digit, and this is the twos digit, and it's a value mod 3. This is the sixes digit. This is the 30s digit, mod 7. If you want to get some intuition for this, replace all these numbers, 2, 3, 5, 7, with 2, and then this will be exactly, the digits of the number in binary, the bits of the number in binary. Okay, so this is what happens when you generalize and have different radix for each position. Okay, it turns out that if you have a way of converting x mod p and x mod q into this expression, like the floor of x divided by p mod q, if you have that, then you can eventually get the number into this mixed radix representation. By doing this, many, many times in the right order, you can get values of this form. Okay, so that's our roadmap to do comparisons, right? The big picture is that we want to compare two integers that are represented in this Chinese remainder residue number system. Okay, so we found this really strange way to do this, and I'll just show you how it works by example. So the input is a number. I'm given x mod 3 and x mod 5, and I want to compute the floor of x divided by 3 mod 5. And just to give you some intuition about what that means, it's this is like the truth table of what I want. Right? So if the input is the number 7, then it's given to me in this format, and I want to compute the value 2. Okay, so we found this weird way to do this. So if you take x mod 3, that's this second row, and subtract the third row, you get something that looks like this. I'm subtracting them over the integers. And one thing that's nice about this is like, look, I'm already done here in the first row. Like the correct answer was 0, 0, 0, and I got 0, 0, 0 from the subtraction. And if you look at this third row, this new row, it consists of a lot of segments that are the same, right? So these three are the same, these two are the same, these three are the same, these two are the same. And the boundaries between these segments are compatible with what we want here, right? So these three are the same, but that's okay because in the final answer that I want, those three should all give the same final answer. So it turns out that you can compute this subtraction. If you take this fourth row, if you reduce it mod 7, that's also fine. So you get values like this, right? So each of these segments that I marked gives a different value here. So now all we have to do is apply a projection. So we are at this point so far in our computation, and we want to get this value, but actually that's just a projection. So project 0 to 0, project 2 to 1, project 4 to 1, project 6 to 2, project 3 to 3, project 1 to 3. So you see, if I just project these values, I can get the result that I want. So overall, the cost for this gadget is, first I need to kind of convert x mod 3 and convert x mod 5 into values mod 7. That costs a little bit. Like that's one of these unary gates. Once they're both mod 7, then I can subtract them mod 7. That's free. And then once I have that subtraction mod 7, I can do this. That means I have this value so far. I can convert it to the answer that I want just with one of these unary gates. That will cost like 7 ciphertext. Okay, overall, if you work it out, it costs roughly 2p plus 2q ciphertext. If you do this between all pairs of primes, it allows you to convert to this primorial mixed radix representation. Yeah, and so if we figure out how much it actually costs when we're talking about 32-bit integers, let's say, I don't know if this is true, but let's say 32-bit integers requires the product of 10 primes. So if you figure out how much this costs for the product of first 10 primes, you get a comparison. This is how much it costs to garble a comparison gate. It's not very good compared to Boolean, right? So there is a trade-off. Obviously, Boolean representation is very efficient to do a comparison. But of course, our method is much cheaper to do arithmetic operations. So I think that is, that's my last slide that I have prepared. So yeah, now you know everything that I know about garbled circuits. You know how to make Boolean circuits efficient, and you even know how to garble arithmetic circuits. I think we have 10 more minutes scheduled, and I'm happy to take any questions and clarify anything that was confusing. So if you have questions, please ask or ask in the chat. I just remembered that there's a Q&A feature, which I didn't have open. So maybe I can start with the question that I can read in the Q&A. I think this was just asked though, so I didn't miss anything earlier. So the question is it faster to convert CRT into, I guess, Boolean for comparison, and then convert the results back? Yeah, so that's definitely something we thought about. So our goal was to have some way of doing comparison. So I think the first thing we thought about was, can you convert back into Boolean and then do the comparison there? And I don't remember how much worse it was. It was a little bit worse than what we got by doing this technique. I don't have a good intuition why, other than the fact that this representation, it involves, it feels similar. It feels more similar to Chinese remainder theorem representation, right? Because you have a residue mod 2 and mod 3, mod 5, and you have the same thing over here. So it's a little bit closer. You just need some positional number system to do the comparison. So that is something we thought about, but we were not able to do, we're not able to convert into Boolean in a way that was better than this. So good, thanks for that question. I think, good. There's a question in the chat, how to deal with input gates for arithmetic garbling. That's good. That's the slide that I skipped. So I actually do have a slide for that. So at the input level of the circuit, you can represent the numbers in binary. There's a couple ways to do it. Yeah, at the input level of the circuit, you can, suppose you have an input wire that is a mod p value. So you can use log of p number of oblivious transfers. So yeah, you have a mod p value, write it in binary, and now you can use an oblivious transfer for each bit of that binary number. And then once it's inside the circuit, so how can I illustrate? Maybe I can find a way to illustrate, because I think the slide was not good. Can you see my screen here? So say you have a number, you have something mod 5. So then you can write, boy, this is dangerous to be doing this live, but let's see if I remember how to count in binary. It looks like I do. No, looks like I don't. So write the number. No, yeah, I only have to go from 0 to 4. Write it in binary, and now do an oblivious transfer to learn either a wire label for 0 or 4. Do an oblivious transfer to learn a wire label that encodes either 0 or 2, and do an oblivious transfer to learn 0 or 1. And then you add these together for free. Inside the circuit, you add these together for free. Now you have this value mod 5 in the way that you wanted. So it's actually very efficient to do that at the input level of the circuit. So a normal Boolean circuit for 32-bit values uses 32 OTs. In our case, it was only 37 OTs. Let's see. How can we make sure that the general gadget costs 2p plus 2q ciphertext? I don't know an easy way to convince you. Well, maybe I could. Yeah, it's a little bit tricky. There is a proof in the paper, but basically, yeah, the important part is this step. The number 7 was important because it was like 3 plus 5 minus 1. So in the general case, this is like p plus q minus 1. So here you pay, like, you convert something mod p into this. So that costs you roughly p ciphertext. This costs you roughly q ciphertext. And then this last step is roughly p plus q ciphertext, because this number is roughly p plus q. yeah, I don't, there's not an easier way to see it than that, because you need to prove that this step actually works for arbitrary P and Q. There's not an easy way for me to say that right now. How do we choose between arithmetic circuits and Boolean regarding practical problems? Are there any recommended papers? I don't know the paper. The best thing I can suggest is, well, there's this paper that I'm talking about here. This is Ball, Malk, and Rosulek 16. I'm trying to find a slide that has the name of the paper. In this paper, we go into some detail comparing the standard Boolean setting to the arithmetic setting. We have a couple different scenarios that we compare. We also have a follow-up paper that is only on ePrint. It's called, the title is something about garbled neural networks are practical. So we try to use this technique to garble neural networks. And we do some comparison between Boolean garbling and this new garbling. I think we were hoping that this would take off a little bit more than it did. I think the problem is that it's really good at additions and multiplications. It was really bad at most other things, especially comparisons. If you think about how a neural network works, there's lots of additions, multiplications, but there's also like a activation function. I'm trying to find this slide. Yeah, there's also like activation functions which use comparison gates, and so those are expensive. So first of all, I'm not sure if people are using garbled circuits for a lot of their implementations. Yeah, so there just hasn't been a good comparison. I think there's a lot more. I feel like we only scratched the surface of this arithmetic garbling stuff. We have this first paper, and then we have some more follow-ups with some other tricks, but I feel like there's many more tricks that are out there waiting to be discovered. Why a random 32-bit value can be represented by a number of primes. So the idea is, I keep switching back. Sorry, I keep switching back between these. Oh, this computer is really slow. It's not happy with me. Yeah, so the idea is we just need to choose a modulus, any modulus that's larger than 2 to the 32. And the modulus that we choose is this one, the product of some number of primes. So every number in this ring can be represented according to its remainder mod 2, remainder mod 3, remainder mod 5, and so on. So it's just the only thing you need to do is make sure that you have the right number of primes so that their product is larger than 2 to the 32. And then everything else works out because of the math of the Chinese remainder theorem.
Okay, just to clarify that the last person who asked this question is not the actual administrator.
Okay. Okay, I didn't even look at the name. Sorry.
Okay. I'm sorry I was like 15 minutes late for the talk, but just to catch up with the row reduction part and on.
Yeah.
Is there any other questions? So I have one question. If so, this free XOR and the half gate scheming. So we can only prove the security in the like random oracle or like collision robust. I'm sorry, correlation robust hash function model. Or we can prove it in the standard model. on the
Right. So in this talk, I just assumed a random oracle. I don't know why I'm flipping through slides. There's no slide that mentions this. In this talk, I only talked about the random oracle model, but you're right. You can prove it from a weaker assumption. Basically, for free XOR, you need terms of this. So values of this form need to look random. If delta, when delta is secret, when you garble the ciphertext, you have terms that look like this and terms that look like that. They need to look random. That's called correlation robust hash function. UU has a nice paper about constructions of these objects, so you should all read that. But this kind of an assumption is required. There's a paper, I remember CKKZ 12 maybe. This is Sengol Choi, Ranjit Kumar-san, John Katz, and Hongsheng Zhou. The paper in TCC about the security of the free XOR garbling. And they say that you definitely need some kind of assumption like that. You really can't prove it from a standard assumption like pseudo-random functions. Yeah, this is TCC 2012, I think.
I see. If there are no further questions, since time is up, we thank Mike for his very, very educational talk. Thank you.
Thanks, everyone.
Okay. Thank you for your time.
We'll do it again next week. Is that the plan still?
Yeah.
Okay. Thanks, everybody. Have a good day.